In yesterday's class, we made use of the two-port network theory to evaluate the performance factors of amplifiers such as input impedance, output impedance, voltage gain, current gain and power gain. These are the important factors, performance factors associated with any amplifier. Taking for example Y parameter, I had shown you how to evaluate the input impedance and ask you to evaluate the output impedance, and I evaluated the voltage gain, asked you to evaluate the current gain and power gain. Today let us see whether you have really understood this. In case you have any difficulty in evaluating this, we would work out the whole thing for the Y parameter case now. I would request you to perform the same calculations for all other parameters in almost identical fashion and see what these input impedance, output impedance and power gain, voltage gain, current gain are in the respective parameters. So, I would like you to concentrate on the method that is adopted here. The same method must be adopted for the rest of the three parameters. So, first let us see how we can evaluate the input impedance. So, we take this equation II and Yi is the self impedance at the input, this multiplied by Vi and Yr, and we have to replace this V naught by something that is dependent upon Vi, so that we can find out the input impedance, which is Zi, Zin, which is 1 over Yin, and Yin is II by Vi. This is the input impedance seen from here. In fact, if Yr is 0, this is same as Yi. If Yr is not 0, this is Yr into V naught, and this V naught has to be replaced in terms of Vi. So, it is necessary for us to evaluate and find out what is the relationship between V naught and Vi. That we can get from the second equation. We know that I naught is the output current here, and I naught is equal to V naught into YL, but the current then will flow this way. So, minus V naught into YL. So, I naught in any of these circuits is always equal to minus V naught into YL. This is always the case. I naught is known in terms of V naught and load admittance. So, because this is assumed as plus minus, the current would have flown this way, and I naught is assumed to be opposite, we put the negative sign. So, substitute this I naught in the second equation. So, we have minus V naught YL equals YF Vi plus Y naught V naught. So, this equation yields the relationship between V naught and Vi as V naught over Vi is nothing but minus Yf divided by Y naught plus YL. This in the last class we had very simply evaluated from this circuit itself. Yf into Vi is the current in this. This current will flow through the total admittance, which is Y naught plus YL. Resultant voltage therefore has to be Yf into Vi into 1 over Y naught plus YL, okay, with a negative sign. That is what we have derived. So, this is an important equation. For voltage gain V naught over Vi. Now, once we know V naught in terms of Vi, we can substitute this in the first equation and get II equals Yi Vi minus okay, yr into yf divided by y naught plus yl. This is this minus yf into y naught by yl minus yf divided by y naught plus yl is the term that we are replacing it with. Into vi is v naught. So now we get I by vi, which is nothing but input admittance of the amplifier is equal to yi minus yr yf by y naught plus yl. An important relationship in the sense that this relationship is valid whatever be the parameter you select, as long as we replace these parameter with the corresponding parameter. That what I mean is, if it is z parameter, then z in is always equal to zi minus zr zf divided by z naught plus zl. If it is h parameter, h in is equal to hi minus hr hf by h naught plus hl. If it is g parameter, g in is bound to be equal to gi minus gr gf by g naught plus gl, and therefore it is immaterial. That is why I introduced the term immittance instead of calling this impedance or admittance. It is immaterial what the parameter is. It is called immittance matrix, and a general term that is used is P. Okay. So you can just say that P in is always equal to Pi minus PR PF divided by P naught plus PL. So now that you know the results in all the other parameters, I would request you to adopt the equivalent circuit approach or the equations to derive these relationship and convince for yourself that this is unique and it remains unaltered in its nature, right. So this is as much about input admittance and voltage gain. This we had derived in the last class itself by some other approach. We will now see the other parameters, other important performance factors associated with the amplifier, which is I naught over II, current gain. Now this can be again derived from the equations, but I would like to do it slightly differently, just as we did it in the beginning of the class on amplifiers. Now that we have evaluated V naught over Vi, why not we evaluate I naught over II in terms of V naught over Vi? That is the best way, because we have solved already all these equations and therefore we know V naught over Vi. So V naught is going to be equal to, we know again in terms of I naught we have got that is equal to I naught minus I naught by YL. This is from this equation. V naught is already known in terms of I naught. Now another important parameter, we also know Vi in terms of II. What is it? Vi equals II divided by Y in. From this we have already evaluated this. Vi is equal to II, this goes there, divided by Y in. Subsequently therefore we have V naught over Vi is equal to minus I naught over II into Y in by Y. Important relationship once again, that is I can either express the voltage gain in terms of current gain into Y in by YL, or now I want I naught over II, therefore is equal to minus V naught over Vi into YL divided by Y in. Is that clear? So, this is a simple way of always remembering how to evaluate I naught over II given V naught over Vi. We do not have to start all over again solving the equation. That can be done independently by solving the equation, eliminating the other variables V naught and Vi from the two equations. So, this is done knowing the relationship V naught over Vi, how to find out I naught over I. If you know this, then the power gain becomes a very simple factor. Now, one word of caution, power. What is power input? Power gain here in general is going to be output power divided by input power. This is one way of defining power gain. There are several other ways, which this is the most common way of defining power gain. Let us now see how this can be evaluated in general. We have done this already for amplifiers. Let us do it for a two-port general network. What is output power? We know that output power is going to be expressed as V naught squared, that is the output voltage, okay, RMS value, V naught squared divided by RL or into real part of what? YL. Because we are talking of admittances now, real part of YL. This is the input power. This output power. Input power is in a similar fashion. What is it? You can now easily see this output voltage squared into real part of YL. This should be input voltage squared real part of what is it? Y in, which is already evaluated. Y in is already evaluated. It is the real part of this that you have to take in order to find out what the actual power that is inputted. So, power gain therefore is the ratio of these two, that is voltage gain V naught over Vi squared, V naught over Vi squared into real part of YL by real part of Y. So, the same thing can be derived for any of the parameters Z, G or H by adopting the similar procedure and similar definitions. So, in summary, I can say that we have understood how to derive for any two-port network the important performance factors of the amplifier. These are voltage gain, current gain, power gain and input impedance and output impedance. These are the 5 important parameters associated with the performance factors, right. So, these can be derived in terms of any one of the other 3 parameters that we have left out, Z, G and H. These are going to be left out as homework problems for you to show that input emittance is going to take the nature exactly similar to this. Now, output admittance, I have not derived that, like we can derive this. Again I must mention that when I am evaluating output admittance, this is something that has not been understood really. I am trying to find out what the output current is. I will remove the load, this is, I will excite it by means of a voltage here which is V naught. This is not the voltage which has been generated because of input, this is a voltage which I am applying here and finding out what this current is. That is the definition for output impedance, V naught by I naught, when I am exciting the output, and then this excitation has to be, this is an independent excitation, this has to be remote. In this case, obviously, if YF is not existent, then output impedance is going to be 1 over Y naught straight away. This is called the self admittance, okay, Y naught. Otherwise, it is going to be determined by this YF and YR, right. YR is absent, okay, again the same thing is going to happen. It is not going to be dependent upon what is happening, okay, at the that is both YR and YF. If they are absent, these are responsible for forward and reverse transmission. If something is applied at the output, this YR should be present, so that it conveys it to the input, and this input is in turn bringing it to the output. So both YR and YF should be present in order to feel something at the output, okay, when I am exciting at the output. If YR is 0, okay, then nothing happens that is transferred from input to output. So this impedance is going to remain as the output impedance. Let us now see what it is. The circuit looks exactly similar to the circuit that is used for evaluating the input admittance. If you notice, V naught is what I am applying here, and I have to evaluate I naught. I naught is given by Y naught V naught. This is the second equation, Y naught V naught plus YF into VI. This VI I have to replace in terms of what? V naught. Then I will get the relationship between I naught and V naught. So because of applying V naught, there is something that is happening here. There is a current that is generated here, which is YR into V naught. This is the reverse transmission. So YR into V naught generates a current here, and because of this, there is going to be current pumped in this, okay, which will generate a VI, and what is that VI is what we have to substitute, okay. So VI is generated here because of V naught, okay. So YR into V naught is the current, and how much is the current that is flowing in this? This current is going to get divided between this admittance and this admittance, okay. So that admittance that is going to take a current from this is nothing but YS here, the source admittance, okay. So what is the current that is going there? That is nothing but YR, okay, divided by YI plus YS, okay, into that's right, with a negative sign, okay. This is going to be the voltage at this point. This is going to be equal to VI. YR into V naught is the current through this. This current is going to flow through the entire admittance, which is YI plus YS, develop a voltage which is VI. Since the current direction is this way, okay, the voltage is going to be plus and minus. That means there is a negative sign that is to be put, and therefore this is equal to Y naught V naught minus YF into YR by YI plus YS. Is this clear? So I naught by V naught is going to be Y naught minus YF YR divided by YI plus YS. You can now compare this with what we got for this is the Y out. this is the Y out. So compare this with what we got for input. Y in is equal to yi minus yr yf by y naught plus yl. Wherever I is there, replace it with O. Wherever O is there, replace with I. Wherever L was there, replace it with S. Okay. And yr and yf also have to be replaced, but since they come as a product, it is of no consequence. It will always remain as yr into yf. Okay. So you can see yr into yf product is going to remain unaltered, okay, in this change. So yi minus yr yf by y naught plus yl is the input admittance, y naught minus yf by yr by yi plus ys is the output admittance. And in the immitance matrix, P out. So this is what we can write. P out is going to be P naught minus PR Pf divided by Pi plus Ps. This is the general output immitance formula. So once again I request you to show that this is the case in the other 3 parameters by adopting either equivalent circuit approach or solving the simultaneous equations. Now let us take an example here to illustrate what we have learnt. For the 2-port network shown, determine V naught over Vi, I naught over Ii, P naught over Pi are in, that is input resistance and output resistance. Now the only difference between what we had earlier worked out in the amplifier case and this, the earlier amplifiers were all unilateral. What it meant was that YR or HR or ZR or GR was 0. So transmission was possible only in one direction, forward direction. Whatever was happening here was not getting reflected onto this side. Now we have put non-idealities everywhere. So here is the case where we have some reverse transmission. Whatever is happening here is felt here. So this, what happens here is felt here, what happens here is anyway going to be felt here. That is what we want in amplifier. What is happening here is to be amplified, but what is happening here should not be reflected here. So we do not want any reverse transmission in a good amplifier, but this is not a good amplifier, there is some reverse transmission here. So under this situation what happens? Let us consider this. Here we have a current source feeding on to the input. Whether it can be represented as a current source or otherwise is justified by comparing the impedances. This is 100K and this is 0.1K. So this is definitely a current source drive. There is no doubt about it. The source impedance is very high compared to what it is seeing. At this point, the control source, this, whether it is correctly represented as a current source or not, can be again justified by comparing it with the load 5K. So 5K is very small compared to its source impedance of 50K. So it is correctly represented as a current source. Now if these are the currents due to output and input respectively, then this whole representation can be identified by comparison with what you have learned with Y parameter. So this is what you should be able to do. That is because here II is equal to Vi divided by 0.1K plus this 10 to the power minus 5 times V naught, that is the total current. That is the equation, one equation. The other equation is I naught is equal to V naught divided by 50K plus 10 to the power minus 2 into Vi. These are the two equations that describe this 2-port now, which is nothing but Y parameter representation of the equivalent circuit. Okay. So obviously I have to now put down the Y matrix for this network as this is the Y matrix. Yi is going to be 1 over 0.1K YR, this is YI, YR is 10 to power minus 5. You can see that this should be a very small factor in terms of Siemens compared to what? Because this is now having a dimension of Siemens. Compared to other parameters, this parameter, these are all Y parameters. So, this should be very small. Then only I can call it as a very good amplifier. If it is 0, it is the ideal amplifier. Right? So, now on this side Y naught is going to be 1 over 50 kilo ohms and YF is the main transmission 10 to power minus 2 Siemens. So, all these are Siemens and you can see that this should be really a large factor compared to this in any case. So, that it is more unilateral. Okay. That means transmission from here to here is more than reverse transmission. Okay. So, these are the factors that. Now, because of these two factors, there is interaction between input port and output port. What happens at the output port is going to be reflected at the input port. Okay. So, the input impedance is going to be different from the original impedance of 0.1K, which is the self impedance. If this is not there, if this is 0, it would have been just 0.1K. Because of this now, it is going to be different from 0.1K. How different it is going to be is what we are going to now see. Let us first evaluate the voltage gain for this. V0 over Vi, this is going to be therefore Yi, this is YR, this is YF, this is Y0 is going to be minus YF divided by Yi plus YL. So, minus YF by Yi plus YL, that is the value which comes out as minus 10 by 10.2. Oh, sorry, Y0. This minus YF by Y0 plus YL. So, which comes out as, this is therefore 50, right. So, how much it comes? So, this is 1 by 50 plus 1 by 5, which is minus 50 by 1.1. Minus 45.45. So, this is the voltage gain. Next, Y in is going to be Yi minus YR YF divided by Y0 plus YL. This factor we have already evaluated as minus 45.45. So, this is Yi is going to be 1 by 0.1 into 10 to the power 3 minus YR YF 45.45 into, that is YF by Y0 plus YL, minus of that is minus 45.45 into YR, which is 10 to the power minus 5, which is going to be, this is 10 millisiemens or 10 into 10 to the power minus 3 minus 0.4545 into 10 to the power minus 3. It's going to be, how much is it? 9.54. Which is to mean that R in is equal to 1000 divided by 9.54, which is 104.8 ohms. Compare this with what we had earlier. It was 100 ohms. Now it has become more than 100 ohms. How did it happen? It was earlier 100 ohms. Why did it become more than 100 ohms? That means the effect of the feedback is such that it is now simulating a negative resistance here, such that the combination of this 100 ohms and what is simulated here, okay, is more than 100 ohms, because if it is a positive resistance that it has simulated, it would have become less than 100 ohms. Okay. So the effect of the interaction of the output at the input here is to boost up the impedance from the original impedance of 100 ohms. Original impedance without any feedback would have been just 100 ohms. Because of this reverse transmission, it has become more than 100 ohms. Why did it happen? Because it is now simulating a negative resistance across this positive resistance and boosting up the input impedance. This is called positive feedback. This is called positive feedback. So why is this impedance more than the self impedance at the input port? That is because it is simulating a negative resistance and effective resistance is more than the original impedance. So this is called positive feedback. How do we recognize that it is positive feedback? What is the factor that was responsible for this? We know that it is YR into YF, okay, divided by Y0 plus YL, which is coming additionally. If this is, assuming that these are positive, this becomes positive feedback only when YR into YF is positive. So we can quickly identify whether it is positive feedback or negative feedback by seeing the product YR into YF. Here 10 to the power minus 2 into 10 to the power minus 5, that is the factor by which, okay, the effect of output is reflected at the input, okay, and it is getting subtracted from the input admittance. That means effective admittance becomes lesser or impedance becomes higher. Okay. So this is the effect of positive feedback. We will discuss more about positive feedback much later, okay, but you should now know that in an amplifier, this, an ideal amplifier, this is not at all wanted. Okay. If YR into YF is negative, then it is called negative feedback. That means negative. What happens then? You can look at it. If this is negative, in this case it is not negative, let us say this is minus or this is minus. If any one of this is minus, then it can be negative feedback. Then what happens? This becomes positive. That means the total admittance increases or impedance decreases. So this is what happens in negative feedback. In this example, we are giving positive feedback here, and that is why the impedance is increasing. Okay. Next, we would like to evaluate I0 over II. I0 is nothing but V0 minus V0 by RL, and II is nothing but Vi divided by Rin. Okay, that is II. So if you know the voltage gain, which is V0 over Vi, which has already been evaluated as minus 45.45, minus minus becomes plus, this into Rin. Rin is also evaluated as 106 4.8, that divided by RL, which is given as 5 into 10 to the power 3. This is the current gain. How much is it?
0.95.
Now this is a good example, 0.9526, where the current gain is less than 1, still it is acting as a power amplifier. It is giving you voltage gain and it is having a current gain which is less than 1. This is quite possible in practical amplifiers. Either it has to give a current gain or voltage gain so as to give ultimately power gain, so that it can retain the name of amplifier, right. So what is the power gain? This is current gain into voltage gain, magnitude of that is 45.45 into 0.952, which is 43.3. As long as the power gain is greater than 1, it is called an amplifier. This is an active device. If the power gain is less than 1, the two-port network can be termed as a passive device of no use, right, for amplification purposes. So power gain has to be greater than 1 in order to treat it as an amplifier, even though this is giving you less than 1 as current gain. It is ultimately acting as an amplifier because power gain is greater than 1. Now we have to evaluate only the final thing, that is R out. So Y naught, Y out is equal to Y naught minus YR YF divided by YI plus YS. This is what we have evaluated earlier. So how much is this? Y naught is going to be 1 over 50 kilo ohms minus YR YF is same as 10 to the power minus 7 divided by YI plus YS, which is 1 by 0.1 K plus 1 by 100 K. We will write it more clearly up somewhere here. So Y out is going to be equal to 1 over 50 into 10 to the power minus 3 minus, now this 10 to the power 3, 10 to the power 3 goes 10 to the power minus 4. So 10 to the power minus 4 divided by 10.01. So this is going to be 10 to the power minus 3 into 1.001. Is it correct? No. 10 to the power minus 4. This is 10 to the power, just a minute, 10 to the power minus 4 divided by 10.01, this is 10 to the power minus 5 into 1.001. So how much is this now? This is going to give you 100 by 50 into 10 to the power minus 5, that is 2 into 10 to the power minus 5. This is very nearly 1 into 10 to the power minus 5. So this is equal to 10 to the power minus 5 Siemens, which is therefore going to give you R out equal to 100 K. Again you will notice the same strange thing that has happened. The self admittance at the output is 1 over 50 K, or the output impedance, self impedance is 50 K, but now because of interaction, okay, from the input it has become 100k, it has increased. That means again this same effect is there because of positive feedback. The impedance level both at the input and the output have gone up. From 50k it has gone up to 100k. That means there has been an effect of negative resistance on this side also. So this clearly illustrates what happens because of this dangerous negative that is reverse transmission factor, which is causing positive or negative feedback. Now we will later see that we can purposely introduce, okay, positive or negative feedback once we understand the amplifier thoroughly. So before understanding the amplifier thoroughly, we must design amplifiers which have no reverse transmission. This reverse transmission is going to play lot of role in later designs, both in negative feedback amplifiers as well as oscillators. Okay. So we will preserve this knowledge for use at a later date. Henceforth we will assume that for all our amplifier discussion, until we again raise it, the reverse transmission is 0. I just wanted to bring this about so as to make it clear to you that this factor is sometimes a troublesome factor in amplifier design. Okay. An amplifier has to be unilateral. It has to transmit only from input to output. There should not be any feedback. It is this feedback which causes most of the troubles faced by designers of amplifiers. So now that we have discussed two-port theory and amplifiers, let us summarize the entire thing. Two-port theory as applied to amplifiers, we would like to understand. We said that there are 4 basic amplifier configurations. They are all called control sources. Amplifier therefore, according to network theory people, are nothing but controlled sources. And therefore ideal amplifiers are the following: voltage controlled voltage source, current controlled current source, voltage controlled current source, and current controlled voltage source. These are the 4 types of amplifiers that can be designed. Now, we saw that these 2 are more basic than these 2, because if you have ideal voltage control current source and ideal current control voltage source, by cascading this with this you can get voltage control voltage source, by cascading this with this you can get current control current source. There is no need for therefore synthesizing these 2 blocks at all. If you have these 2, you can obtain ideal amplifiers of all the 4 categories. So these 2 are more basic than these 2. This is called voltage amplifier, traditional voltage amplifier. This is called current amplifier. This is a voltage controlled current source. This is called it's a current source. So admittance amplifier, or more popularly called transconductance amplifier. This one is called impedance amplifier. or more popularly called trans resistance amplifier. This is what we have discussed. Then we said an ideal voltage amplifier has a matrix representation which is 0, 0, 0, whatever it is, okay, and has a voltage ratio which is K, something like that. So obviously this voltage ratio comes only as basic definition in G matrix. So G parameter is the only parameter which can represent a voltage amplifier. What does it mean? What it simply means is, if I try to represent, okay, a current amplifier or a trans admittance amplifier or trans impedance amplifier in terms of G parameters, okay, these will go towards infinity, any one of these three, okay. So ideal amplifier, these things will become meaningless, okay. Only in G matrix this can be meaningfully represented, and these parameters should go to 0, and this is the only transfer. So that defines a voltage controlled voltage source. If you see this here, right, this will define G I, which is going to 0. That means the impedance is infinity, right. This G, okay, is going towards 0, that is output conductance. So it is a voltage source. No, it is unilateral, so no reverse transmission. So these things are going towards 0. Again, this is the representation. Therefore, for current amplifiers, the dual of this, that is only H parameter is the only parameter which is suitable for representation. No other parameter is suitable for. I mean, you can represent a non-ideal amplifier by any one of the four. But once you recognize the source impedance and load impedance, you will recognize that particular thing as a particular amplifier, right. And therefore, you must adopt the proper parameter for analysis. Then you would know an idea about the magnitude of these. These will go towards 0, and this is the only parameter which is going to be realistically large. Then trans admittance amplifier. So you can see this. Voltage controlled current source, again this will be 0, okay. The current source magnitude I is going to be represented as Vi into G. So this is going to be conductance, okay, or admittance. So this is going to be represented by Y. The other one is going to be 0, 0, 0 R or Z. So this is going to be appropriately represented by Z. So this is the summary of what I was trying to impress upon you by trying to correlate the two-port theory with amplifiers. This you must remember as the basic theory necessary for you to understand the concept of amplification itself. And these factors being 0 indicate the amplifier to be unilateral. That means no what? Feedback. So these let us say PR, okay, being 0 in any one of the four indicate the unilateral nature of the amplifier where no feedback is there. And PR into PF, the sign of this indicates whether it is positive feedback. If it is positive, negative will indicate that it is negative feedback. More about this feedback we will learn later.